So, we will continue with our discussion on the eutectoid transformations. We took up the case of the steel, which is a easy and more commercial example for us, where the gamma gives you alpha plus Fe3C, and in this we see that depending on the temperature at which this transformation is taking place, where the gamma giving alpha plus Fe3C, there are different types of products that are possible, different morphologies that are possible, and each morphology has certain name given to it. The lamellar morphology is what we call it as the Pearlite, and you actually get this usually at higher temperature, at temperatures closer to the A1 temperature, closer to the transformation temperature, when the undercooling is smaller. When the undercooling is larger, okay, you end up into the domain which is, if this is the A1 and this is the start, this is the finish of the Pearlite transformation. If you are somewhere, if your undercooling is somewhere here below the nose, then you end up into another type of morphology, which is what is called the acicular morphology, where you call them as either upper bainite or lower bainite. Okay. In fact, if you take some hypoeutectoid steels, it is possible that if your undercooling is high, then you may not even get a let us say the proeutectoid phase. We all know that if I take a steel with, let us say, a composition like this, this is 0.8 our eutectoid composition. If I take something like 0.6%, in principle this alloy, as you cool from gamma, it gives you alpha plus gamma first, and then this alpha plus gamma, as you cool down, the amount of alpha will increase, and once you reach this temperature you will have some alpha plus gamma, and the gamma will undergo this transformation. This is what is known to us. But if you have cooled this gamma very fast to some temperatures low like this, then you may see the situation that you actually may not even get alpha, directly the gamma may undergo a transformation. For example, if you look at this, mind you, if you carefully observe this particular start of transformation and the end of transformation, both of them, as you come closer to the transformation temperature, they almost become parallel to the transformation temperature. What does that indicate? Yes, it indicates that the incubation period increases significantly. In fact, the incubation period, as you reach the A1 temperature, it actually becomes infinite. That means the start of transformation itself, okay, takes an infinite time. Why does this happen? Undercooling is less. When the undercooling is less, what is less? The driving force is less, and if the driving force is less, then the activation barrier is high. So, at transformation temperature the undercooling is actually 0, that means the driving force is 0. For the gamma to transform to the Pearlite, in fact at A1, if I draw the free energy composition diagram, how does it look like? You have an gamma, you have alpha, and somewhere here let us say you have a cementite. I mean, let us say this is pure carbon going that side, or if you want to take this as a cementite, you put cementite here, it is up to you. So, this is the free energy of the cementite, let us say. So, at the A1, which is the eutectoid temperature, in principle this is the type of the situation, and once that is the situation, if I am considering an alloy of eutectoid composition, if I am choosing the alloy of eutectoid composition, there is no driving force for the alpha plus cementite to come, because all of them are on the same tangent. So, once there is no driving force, obviously the activation barrier is infinite. So, in principle there is no transformation possible, and that is indicated by the TTT diagram going parallel to the transformation temperature. This is true for this or this particular line which we have drawn. This indicates the formation of alpha from the gamma as you cool the pro-eutectoid phase in this particular case. So, this is gamma plus alpha. That is the reason why, in fact, if you carefully observe, have you ever checked what is the difference between a steel which is annealed and a steel which is normalized in terms of the microstructure? Can you tell me? A 0.6% carbon steel, I am not taking, let us say take a 0.8% carbon steel and tell me what should be the difference. Yes. No, I am asking you microstructure difference. What will be the difference in the microstructure of a 0.8% carbon steel which is annealed and which is normalized? Prerna, do you know? Normalized sample. Anything more? The interlamellar spacing in the pearlite, within the pearlite, is coarser in the annealed sample and it is finer in the normalized sample. Why? Because the nucleation rate is higher. Why nucleation rate is higher in a normalized steel? Whenever I normalize a steel, basically I am cooling it faster. Okay? You imagine that this is the cooling, this is the TTT diagram, forget about the alpha plus gamma, just for the time being you ignore that this is existing, and I am taking a steel above the A1 and I am cooling it. Let us say these are the two different cooling rates. If these are the two cooling rates, one is, let us say, corresponds to the annealing, one is corresponds to the normalizing, let us say. What is the difference between these two cases? You will see that the one which is the annealed one intersects the TTT diagram at this point, and the normalized one intersects the TTT diagram at this point. Once this happens, then you would see the difference between these two is the extent of undercooling. If you look at this, the extent of undercooling that the normalized steel has gone through is different from the annealed steel. The undercooling is smaller for an annealing and larger for a normalizing. Even physically also you can understand that when you are cooling it very slow, the transformation occurs near the transformation temperature. When you are cooling it very fast, the system gets undercooled because of the inertia in the system. Why does this inertia come into picture? Because a product phase has to be nucleated, it needs diffusion. Alpha plus Fe3C has to nucleate, so that means a critical radius has to form, that means you need certain time. If you are not providing that time, the gamma will tend to keep on remaining as gamma until a certain lower temperature where it starts transforming. That is the reason why you will see a normalized one will have a higher undercooling than this. The moment you have a higher undercooling, automatically a lot of nucleation kinetics come into picture. We have discussed this a number of times. So, when you have a higher undercooling, obviously the activation barrier is smaller because the driving force is larger. The higher the undercooling, the driving force is larger. In fact, what would happen to this? The higher the undercooling, the gamma curve will be much above the alpha plus cementite. So, as a result, for the same alloy composition, I can see that the driving force will keep on increasing. This will get shifted. Why? Because as I come to lower and lower temperature below the A1, gamma is less and less stable, and the alpha plus Fe3C mixture is more and more stable, because we are below the eutectoid transformation temperature. So, if at all gamma is remaining below the eutectoid transformation temperature, it is only metastable gamma, that is it. So, it cannot in principle remain as a stable gamma, it is only metastable gamma. So, that is why all this that you see here, all this gamma that you see until you reach this MS temperature, this whole left of this curve is all metastable gamma. Gamma is there, but it is not a stable gamma. So, in principle when I simply just use two different cooling rates, I am getting two different undercoolings, and because of the two different undercoolings, obviously the activation barrier is low, the nucleation rate which is related to the activation barrier exponentially is also going to be very high. So, I, which we know A into exponential minus delta G star by RT. So, as a result you will see that if the activation barrier is small, then the nucleation rate is higher. If the nucleation rate is higher, then you will see interlamellar spacing will come down. So, that is the reason why in a normalized steel you see a smaller interlamellar spacing, in a annealed steel you see a larger interlamellar spacing. In addition, you would also see one more difference. What else? Pearlite colony size again is going to be smaller. The number of nuclei, here when I say nucleus, it is a pearlite colony gets nucleated, it is not a simple one single phase getting nucleated, one pearlite colony is getting nucleated. So, when I say nucleation rate is higher, a number of pearlite colonies are getting nucleated within a particular grain. So, one grain is broken into a number of colonies if the undercooling is higher. If the undercooling is smaller, you will see it is going to be less number of nuclei, that means bigger colony size. So, colony size and the interlamellar spacing, these are the two basic differences that you see in a normalized and in annealed. This is as far as it is a 0.8 carbon steel. The moment I make it 0.6, what will be the difference now? These two are anyway going to be there, whatever two differences that we just now talked about it. In addition, something else would be different. Amount of hypoeutectoid phase is going to be smaller in a normalized case when compared to a annealed case. That means basically if I am cooling it faster, this particular temperature difference, which is what we call it as, what do we call that? This, there is a name given for that range, this, what is it called? From here to here for a given steel, it is called intercritical range. Because these are the two critical temperatures. What is this temperature? A3, A1, A3 and A1, whether it is C or R depends on whether you cool or heat, let us not bother. So, this is the A3 temperature, this is the A1. So, between A3 and A1 is what we call it the intercritical range, okay. And that range there is certain amount of what is called some temperature difference between the A3 and A1. If I am cooling it faster, the time taken for crossing this range is going to be shorter, and once that is the case, the probability of gamma coming out, because you are crossing that very fast, that particular intercritical range. If you are crossing it very fast, the probability of the time available for the alpha to come out of gamma is going to be smaller. So, when you are cooling it faster, the amount of the what is called the proeutectoid ferrite, or if you are on the other side proeutectoid cementite to come out will be smaller. So, in fact if you keep on cooling it faster and faster, you would even see a situation where you may not get the alpha at all. So, for example, if I use a cooling rate something like this, you do not intersect this alpha plus gamma region at all. If you do not intersect the alpha plus gamma region, this alloy which you are cooling like this would not give you any proeutectoid phase, it will straight away give you some pearlite, but at the same time because this cooling curve is not intersecting this, because it is not intersecting this, then you will see only some amount of gamma will transform to pearlite, the remaining gamma will be left out, and once you reach below the MS, that remaining gamma will undergo a martensitic transformation. So such an alloy would not give you any proeutectoid alpha, it would simply give you pearlite plus the martensite, and instead if I cool it to high temperature like this and hold it there, then the same gamma would undergo a martensite a bainitic transformation, whether it is upper bainite or lower bainite, and if I hold it for a shorter time and then cool it, then you will get a what? Bainite plus martensite, not pearlite plus. If you hold it here and then quench it, then you get a pearlite plus martensite. If you hold it here and then quench it, you will get bainite plus martensite, because below the nose, okay, we have already discussed yesterday that the morphology of the ferrite is different, you do not get lamellar. So it, because of the diffusion problem, the gamma first gives you alpha of the same composition as that of the gamma. So it is a polymorphous transformation followed by precipitation, whereas here it is first actually it is cementite coming out and then alpha coming out. So that is the difference between this and this. So that is why you get a lamellar alpha plus cementite mixture here, and if you have not crossed the end of transformation, and if you are, in fact one can draw a number of other isotherms here, okay, other if you call this as for example call this as start of transformation, it means 0% transformed. If you call this as end of transformation, it means it is 100% transformed. Between the two we can draw a number of other seekers which indicate different percentage of transformation. All of you possibly know how we get this TTT diagram. You basically take a steel of a number of samples which are all austenized there and then brought to a particular temperature. At that temperature, at different regular intervals, you take out the steel and then quench it and then look at the microstructure, or indirectly you measure the hardness, which is an indicator of the microstructure. So in principle the microstructure is much more accurate. So you keep on seeing the microstructure. For example, if a steel is quenched from here itself, what would you get? You get a 100% martensite. If a steel is held up to this time and then quenched, then you would have some of the gamma would have transformed to pearlite and the remaining gamma would give you the martensite. And like that, if I keep on holding for different times like that, you would see once I cross this line, I would not get any more martensite. Why not? I am crossing the MS temperature while quenching, because there is no gamma left out, and we know pretty well that pearlite cannot transform to martensite. Why pearlite cannot transform to martensite? It is already, pearlite is already stable. No, that is austenite is also stable, okay, of course at a different temperature. It is not that the reason why pearlite cannot give you martensite. Yes, yes. So martensite forms by a shear transformation of one structure to the other. That is why the FCC structure of the austenite shears and gives you martensite, whereas when you are talking of pearlite, it is already a two phase mixture with two different structures and two different compositions. So such a two phase mixture cannot shear and give you one single phase structure. So that is the reason why a pearlite cannot. So if I have a pearlite and I want to get a martensite, what do? I have a pearlite and I want to get a martensite out of it. Again re-austenize it and quench it, that is the only solution. If I have a pearlite and I want to get a martensite out of it, the only way is re-austenize it, heat it back to above A1 and then hold it until all the pearlite gets converted to the austenite, and then from there you quench it, and depending on your quenching rate you either get a partial Martensite or a full Martensite, depending on whether it is intersecting the starter transformation or not intersecting the starter transformation. But if it intersects the cooling curve, if it intersects the end of transformation, there is no chance for you to get a Martensite. Once the cooling curve, any cooling curve that you adopt, if it intersects the end of transformation, the moment it has intersected the end of transformation, that means the transformation is complete, gamma to pearlite. When we say transformation, we are talking about gamma to pearlite transformation, that is complete, and once that is complete, then obviously even though I say, sir, I am cooling it and then coming below ms, it is of no use, already transformation has taken place. This is similar to saying that, sir, I take a liquid, bring it below Tg, why glass is not forming? It depends on whether before you bring it to Tg, whether it has formed crystal or not. If it has already crystallized, then that crystal cannot give you a glass. Crystal can still give you not a glass, but an amorphous structure under different circumstances. Can you tell me when? A crystal can become amorphous. Have you ever heard of such situations? Yes, ball milling is one, irradiation is one. Basically you have to break the crystal structure, you have to destabilize the crystal structure. How do I destabilize? I introduce a lot of defects into it, so that this crystal with lot of defects becomes unstable, and at some stage it cannot remain as a crystal and undergoes a transformation. We call that as an amorphous material, we do not call it as a glass. Glass is a term which is specifically reserved for a liquid to solid transformation, because the reason is, when you take such a glass, because it has come out of the liquid, when you are heating this glass, you start seeing first a glass transition, where this glass, that is what possibly you have seen when we talked about it earlier, that for example, if I take a glass and then do a DSC, this is what you get. I am heating a glass, this is delta H versus temperature, enthalpy evolved versus temperature. If you do that, the glass first gives you a liquid, and this is what kind of a transformation? We already talked, possibly it is a second order transition, and in a second order transition, what do you see? Delta H is 0, delta H is 0, because delta H is 0, you do not see any peak there, okay, you just simply see a step. And now once this supercooled liquid is crystallizing, you get a peak, and the area under the peak tells you how much is the delta H evolved or absorbed during any particular transformation. And this particular region from here to here is what we call it as delta Tx, which is called supercooled liquid regime. Okay. So, where you have the glass is no more a glass, it has become a liquid, but the liquid is still remaining as liquid, it has not yet crystallized. So, it is like a liquid state. That is the reason why many people are doing a lot of deformation in this domain, metallic glasses, and then getting superplastic deformation. Glass, we all know it is a brittle, but the same glass can be superplastically deformed if you are in this domain and get any shape that you want. So, many people do that. In fact, all the shapes of normal glasses that we talk about also are more or less done like that. In a liquid state they do it and then freeze it. So, similarly here you can do that, shape it and then further heat it if you want, so that you can crystallize, and in fact you can control that crystallization by controlling the temperature and time of crystallization, so that you can induce nanocrystals in a glass. And a lot of people have shown that when you induce nanocrystals into a glass, you can make the glass very tough. People have shown that a typical windshield of a motor vehicle like a car will not crash into pieces when there is a crash, whereas it simply bends and goes back. There are examples like that, where basically you induce small nanocrystals, so that a small shear bands form, and then there is no growth of that. So, because each particle will act as an obstacle for the shear band to grow. So, as a result you have some kind of an obstacles for any crack propagation, and that gives you higher fracture toughness. Fracture toughness is always related to either crack initiation or crack propagation. If you can make the crack either initiation more difficult, how do you make the crack initiation more difficult in a typical metallurgical scenario? We do some things in steels, let us say you want to make the crack initiation more difficult, what do you do? Reduce inclusions, okay. Harden the surface, yes. Short peening, there are many things where people try to see compressive stresses on the surface, okay. Hardening is one way, even inducing compressive stresses on the surface, so that there is no fatigue life, for example. Everybody knows fatigue life increases when you do short peening, so it is simply that. So you either make the crack initiation more difficult or crack propagation more difficult, one of the two. If you can do that, you can make a material tougher anyway. So that is yeah. Yeah, this is when we come to Martensite we will talk about it, okay. So there is also always something called deformation induced Martensite, okay. You can, the MS temperature can go up. All of us know that MS temperature, whenever you add alloying elements it always goes down. Why does it go down? Again when we come to Martensite we will talk more about it. Basically again shear is made more difficult, because Martensite transformation is a shear transformation. Whenever you have alloying elements present there, because of the strains that are there around each of the element that is sitting, you would see the shear becomes more difficult, and when the shear becomes more difficult MS goes down. We will talk about it when we come to Martensite transformation. Anyway, coming back here, so there are possibilities where you may not even get a ferrite, a pearlite phase, and straight away get a pearlite, and depending on the actual cooling rates that we are adapting. Fine. So to start supplying carbon atoms to Fe3C and alpha, okay, the Fe3C needs more carbon atoms. So you need carbon atoms to diffuse from the gamma, which is here, into this. At this temperature that diffusion can be very difficult, because you need a longer diffusion, because from the whole of the gamma grain the atoms have to start moving, and that, because it is difficult at lower temperature, this pearlite whatever has formed will not grow much. It may grow, but at a very slow rate, but at the same time the gamma that is there is not stable at that temperature, because you are far away from the A1 temperature. So this gamma has to somehow transform, so as a result new nucleation events will occur. So this gamma, which is now, in fact this gamma will be already depleted in carbon. You are starting from 0.8 carbon, let us say, but this gamma will not be 0.8 carbon, because already some pearlite has come out of it, because some pearlite has come out of it, some carbon has come out of it. So there is a possibility that some depletion might have taken place. Otherwise if we think of it, other way to look at it, pearlite, though there is cementite and ferrite, the overall composition of pearlite is always 0.8, isn't it? When I say here you have pearlite coming out, what is the composition of pearlite if somebody asks, though it is a stupid question because it is not one single phase. If you say what is the composition of pearlite, then basically it is 0.8 only. Only thing is the fraction of alpha multiplied by the composition of alpha plus fraction of cementite multiplied by the composition of cementite should become equal to 0.8. And if you call this as the pearlite, where alpha and cementite is there, so the overall composition of the pearlite is 0.8. So it is because gamma of 0.8 is giving you this. So we can say that this pearlite would have 0.8, but some regions of gamma will be left out. That gamma, because it is not stable at that temperature, it wants to nucleate something, and that is where you would see this gamma would undergo a polymorphous transformation and gives you alpha in some other regions of alpha of gamma, and that particular thing will be a basically in a acicular nature, and depending on where you have actually held it, that may give you either lower bainite or upper bainite. Though academic exercise, there are a number of people who have tried this out and seen a mixture of lamellar and acicular structures. This is possible. Okay. We have talked about it yesterday. Upper bainite is one where if you look at if you think of an acicular structure like this, in an upper bainite the cementite will be precipitated here. This is upper bainite where all the cementite particles will be at the grain boundaries. In an acicular ferrite, this is all alpha, whereas in a lower bainite the same acicular ferrite will be there, but in the acicular ferrite some kind of things like that. In that acicular ferrite you will have cementite nucleated on a certain habit planes. They are like plate like cementites formed inside the ferrite, and this ferrite is formed by polymorphous transformation. So at the time of transformation this ferrite will have the same composition as that of the gamma. If it is 0.8, it will be 0.8, and that carbon, excess carbon will be rejected out and then will be given in the form of cementite, so that at the end of the transformation is over, then the alpha will come back to the original alpha composition decided by the phase diagram. Okay, whatever is the alpha composition at that particular temperature, you will get that, whereas the remaining carbon, the excess carbon will be converted into the cementite. But if this process is not complete, you will always have possibly some excess carbon left out in the ferrite, so that it will remain as what is called a supersaturated ferrite. So you will always have some supersaturated ferrite, because if the temperatures are very low, let us say, and if you have a lot of alloying elements in the steel, the diffusion rates being very slow, you may have always a situation where some supersaturated ferrite will be left out. The complete transformation has not taken place, but provided if you have plain carbon steel and if the transformation is done at relatively higher temperature for a long time, then you would see complete excess carbon will come out as cementites, and you would see the ferrite having, let us say, 0.025 composition, and the cementite will be there according to the volume fraction that it is supposed to be there. Okay. This is how you would see transformations taking place. Second thing is, if we look at this, we also talked there is a possibility that if I take an alloy of this composition, we just now said there is a possibility that it will directly give you pearlite instead of giving you a ferrite. That can happen provided if I extrapolate this, these two lines. What are these two lines? What is this line? A3, and this is ACM. Again there is a mistake here, this has to be steeper. Why that is steeper? ACM line is steeper than A3 line. Can you tell me why? That is also a phase transformation. Gamma is giving you a cementite, there is a phase transformation. Simple geometry, that is it. you should know that here A3, what is this temperature? 910 let us say. So from 910 it is coming to 723 in 0.8%, am I right? And where does this go? 1130. So from 1130 to 723 it is happening in how much? 1.2%, as simple as that. So if you divide that you will get the slope of it, and obviously this slope is higher than this divided by this, if I put it, you would in principle get the slope of that, because from 0.8 it is going up to 2%, from here 0.8 it is going to 0, so this total is 0.8. So as a result, that is the reason why we always say in the hypereutectoid steels, if you want to go to the single phase gamma region, you need to go to very high temperatures, whereas in case of a hypoeutectoid steel you need not have to go to very high temperatures, the highest you have to go is only 910, whereas here as you go closer and closer to 2% you need to go beyond 1100 degrees. At 2% actually it is 1130. So if you are something like 1.4% carbon steel or something like that, tool steel is there 1.4% carbon or 1.5% carbon, such a steel you need to go to very high temperature, and that has its own problems. It has certain advantages, certain problems. What is the advantage, tell me? If I heat a steel to very high temperatures, what is the advantage? Physical metallurgy, if you are thorough you will know. Yes? Coring, why are you talking of coring? Why we are coring will be decreased, you are talking about. Okay, let us not bother, we are talking about heat treatment, in terms of heat treatment, in terms of the microstructures, coarser grains. So toughness will be better, coarser grains, hardenability is higher, you will get a higher hardenability if I take it to a higher temperature, because the grains are coarser, the number of nucleating sites for pearlite to form are lower, obviously the pearlite formation, it is like when we talked about glass formation we said every liquid would form a glass unless crystallization is intervened, this is what we said. Turnbull has made this statement long back. Liquid wants to become a glass because it has no problem in becoming a glass, because its structure is the same, but unfortunately some crystallization is coming in the middle. If I can suppress that crystallization I will get the martensite, I will get the glass. Similarly here, if I can suppress the pearlite formation I can get the martensite, isn't it? So in order to get a martensite you need to suppress pearlite formation. So whatever mechanism, methodologies that you can adopt to somehow suppress the pearlite formation is good for you. So one such methodology is increasing the grain size, but there are problems. What are the problems? If I grain boundary oxidation, okay, fine. If I am not if I am doing my annealing or austenizing in a reduced atmosphere, you won't have problem of oxidation, but still there is a problem, strength decreases, okay, coarse grained strength decreases, fine, toughness decreases, okay. One more, you get more quench cracks when you are quenching to get martensite, because you are quenching from a higher temperature, thermal shocks are more, so that is the reason why. So that to tool steels, so there is a possibility of quench cracks, that is the reason why tool steels you do not quench them. Luckily because the carbon is higher, the hardenability is higher already. Why hardenability is higher if the carbon is higher? Again diffusion problem, whenever you have a high carbon steel there is a more stress inside. If you take an austenite with a 1.5% carbon, austenite with a 0.4% carbon, if you are comparing these two, you would see that because of a large amount of interstitials are occupied by these carbon atoms, the diffusion is more difficult. Each carbon atom would be an obstacle for another carbon atom to move. It is like having too many dislocations, you have a work hardening taking place. So similarly here you have diffusion gets basically any alloy diffusion or chemical diffusion, not self diffusion. Chemical diffusion is going to be more difficult if you have the solute content is higher. That is why chemical diffusivity is always a function of, if you read about diffusion, is always a function of composition. The dilute the alloy is, the higher the diffusivity is. The more concentrated the alloy is, the lower the diffusivity is. So that is one of the reason why diffusion rate comes down, and once the diffusion rate comes down, the hardenability is higher. Of course there is always something which is counteracting this. What is that is counteracting? Because when you take a high carbon steel, there is a pro-eutectoid cementite coming out, and the pro-eutectoid cementite, the moment it comes out, it can nucleate pearlite. So there are always issues like that. The moment you are, that is why, you know, interestingly, if you ever have seen the TTT diagram, in principle, if this is the TTT diagram for a 0.8% carbon steel, I am only drawing the start of transformation. If I take a let us say 0.4% carbon and 1.2% carbon, so I decreased by 0.4, I increased by 0.4. Look at the TTT diagram, how will it look like? How will the start of transformation, that curve look like? Okay, you forget about that. I am not going to talk about pro-eutectoid. I am simply going to ask you the eutectoid C curve. The C curve related to the eutectoid, will something happen to it? Will it shift for that matter? If it shifts, in which direction it will shift and how will it shift? I want you to think about it and maybe draw it and bring it in the next class. Do not consider any alloying elements, nothing. I am not even concerned about the pro-eutectoid, simply 0.4 and 1.2. What would happen to the TTT diagram? Both sides cases, I mean, you try it, till 0.8 it shifts to the right, yes. They do not observe the shift after 0.8. It is very interesting, from almost 0% carbon, if you start looking at and start increasing the carbon content, I can give you the answer here itself. So if you look at from 0% carbon, if you start looking at, I mean 0 we do not consider, let us say 0.1% carbon or something like that, you would see slowly the TTT curve shifts to the right until 0.8, because you are increasing the carbon content, hardenability is increasing, and also in another words also amount of ferrite is also decreasing. So the number of nucleating sites are also decreasing, isn't it? Amount of pearlite, as you go towards the 0.8% carbon, the amount of pro-eutectoid ferrite is decreasing. Once the pro-eutectoid ferrite decreases, the number of nucleating sites for the pearlite also decrease. So that is the reason why you will see maybe a 0.1% carbon would be like this and 0.8 would be like this. Now if I am increasing it further, what would happen? It would actually start coming back. But there is, this is where the question is, there you have two counteracting effects, okay. So in this particular case you do not have that. In the hypoeutectoid you do not have that problem. If I decrease the carbon content, I am decreasing the carbon content, I am increasing the ferrite amount, both are detrimental for hardenability. Whereas if I am increasing the carbon content beyond 0.8, I am increasing the carbon content which should actually increase the hardenability, but I am getting cementite which should be detrimental for the hardenability. So you have two counteracting effects, and as a result actually you do not see significant shifts. What Sriram said is right, you do not see significant shift, because whatever you lose because of one, you gain because of the second one. So you do not significantly see shifts, whereas you see significant shifts on the hypo side. So that is something which you need to understand. So as if you do not understand that, you would not be able to understand the hardenability effects in different compositions, and this is very important. Okay. So what I am trying to say is, if you take this alloy, if the moment this alloy intersects this, if your undercooling is sufficient such that this alloy is brought below that, then you would suddenly get a pearlite, because now you are below that cementite ACM line. So cementite can nucleate out of that. The moment cementite nucleates, immediately you will get a ferrite next to it, and that is what is pearlite. So you can get things like that, and if the temperature is too low, there you would get a bainite instead of a pearlite, but you would get one of the two phase mixture, either a pearlite or a bainite you would get if you are below that, provided nothing has happened before it. Okay, we will stop here.